Okay, today we'll first finish voltage regulation control section, and we can start a little bit on the small signal stability analysis section. So this slide was shown on Tuesday on available approaches to do the voltage control if you're not using generator. So we mentioned there are two categories. The first one is passive voltage control equipment. The second is more active. So passive will be basically just based on the combination of either capacitor or reactor in shunt or series connection. On Tuesday, we finished the two capacitors, the shunt capacitor and the series capacitor. We also somehow mentioned the series reactor or shunt reactor. And you may have some question, under what situations do I need to use, I really need to use such a capacitor or reactor? Or maybe under what condition I need to switch any of them in to the system to support the voltage or limit the high voltage, and what condition I need to switch it off. You cannot just keep it there, right? If your system conditions keep changing. So we need to first answer that question. So that will need to introduce this concept, the surge impedance load. So who have not heard of this concept? Did you take my 421? You heard this one, right?
Oh, right.
Okay. Try to slide. So I'm sure everybody know what it is, right? So so L and C is the total inductance, the total capacitance of a transmission line. So if you do this simple math, you get a real number. Even we use Z, it means impedance, but it really means resistance with power factor 1. So if your load has load impedance exactly same as this one without any reactance, without the imaginary part, you'll be lucky. You don't need to do any voltage control. So because the transmission line, if we consider the series reactance along the line and also the capacitance to the ground, the capacitance will provide some reactive power, and the series reactance will consume some reactive power. So those two reactive power will be opposite to each other. They perfectly compensate. And then for such a line, if you measure the reactive flow, is 0 on both ends. You don't need to do any control. Okay, so I don't go into the detailed derivation, but you can check your slides. If you don't find it, I will let you know on which page. Okay, so which is very important index to judge and what condition I really need to bring those compensators, either reactors or capacitors. So if a power line operates at the surge impedance load with load impedance equal to ZC, calculated by that formula, and power factor is 1, and the VAR reactive power required by the line inducting exactly opposite by the VAR supplied from the line capacitance everywhere along the line. Which means if your load is much higher than this value, you need a shunt capacitor. If it's much lower, you need shunt reactor. Okay, so that sometimes depends on the voltage level and also the length of the line. Here is one example. So the X is actually the distance of the line. So you see, maybe let me bring my pen. So this is like sending end. So I use sending end as the origin, and here is the receiving end. So now assume this line has 600 kilometer for the length, which is 1/8 wavelength. Wavelength means just wavelength of the speed of light, or speed of electromagnetic field propagating within the conductor. So if you operate a 60 Hertz system, so you calculate speed, the speed of light divided by 60, that will be the wavelength. And this case assume the transmission line is 1/8 of the wavelength, which is 600 kilometer long. But that is actually much longer than any practical transmission line. Usually we define maybe around 80 kilometer. Less than 80 kilometer is considered a short line, and longer than 80 kilometer, but less than 250 as a medium line. So you can assume like most of line will be shorter than 200 kilometer, which will be about here. All right, so it has different conditions. So if you have a short circuit at the end of the line, and the voltage will almost like linearly declining of following this straight line. If you connect it to a rated load, so voltage will decline. Okay, now linearly, within 200 kilometer, it can just decline. Maybe it's still a lot. So it's not good to have a very long transmission line. So, but if you have a short line, the concern will be smaller. If you have the load which is exactly equal to certain impedance load, the voltage everywhere is flat, no matter how long this line is. If you have no load, let's say you just want to do maintenance, open one end, so the other end will have very high voltage. Okay, so in reality, most of the line, definitely it cannot be as long. This like a 1/8 wavelength, but the voltage will changing depend on what condition you have. It can be a short circuit condition, the rated condition, heavily loaded condition, light loaded condition, or no load condition. Okay, so the voltage will have large variation. Then you need to decide whether I want to put both like shunt director or maybe shunt capacitor there. Okay, so if over voltage is not big concern, but the low voltage can be bad, you can put shunt capacitor. But you may ask, how about let's just design any line, make sure the length to determine the certain impedance load, and which is about the load I'm going to support. But that's very hard because from this table, if you build, because that, first of all, that value doesn't depend on the length of the line, only depend on the L and the C. And the L and the C doesn't depend on material. Somehow depend, but depend on the design, but mainly L and the C depend on geometry of the line. Okay. But based on this table, if you have a 765 kV line, that's a very high voltage line. So the certain impedance load is 2,280 megawatt. You cannot believe, maybe if you can build this very long transmission, they're delivering 2 gigawatt load from one point to another point. But what if the load decreases or the line needs to be open? So voltage can be very high. So over voltage issues can be more common for high voltage long transmission line. But for short lines, you may have like under voltage problem. I'm talking about just typical load. Okay, so it's not easy to have your actual load be equal to certain impedance load. Then you need to check your loading versus the certain impedance load to decide which one you need to switch in, or which one need to be placed there. All right, that clear? Yes.
There's a transformer in between. Does that get included in the L of the TC? Is that a part of the total impedance of the line?
Yeah, that's a good question. So that will be discussed in the next slide. What do we have transformer? First of all, when you add a transformer, it doesn't change transmission line, which means whatever that transmission line has is still there. But voltage can be controlled by a transformer because you have type changer. If you move up, voltage on that side will be increased. The secondary side, if you move down, it will decrease. Okay.
If I wanted to use this if load greater than SIL formula, then I would include the L of the transformer in that.
You should not include transformer because transformer is a different thing. This is talking about how the voltage is distributed along the transmission line. If it's near the certain impedance load, that will be perfect. Yeah. Okay, how about transformer? So if you have an on-load type changing transformer or under-load type changing transformer, which means it has a tap, which can either move up or move down. Move up, you can imagine the secondary side will have higher voltage, otherwise will lower voltage. How do you decide when to move or how much to move? You can design a closed loop control system similar to the excitation system. Okay, for excitation system, you measure the voltage and compare to the setting point. If it's lower, then you just move up. Okay, And you can also add this component, which is very similar to the load compensation component you have, such as you can program RCXC there, and RCXC just basically this one give you an estimation about the distance of the location you want to control the voltage. Okay, but definitely this RCLC can either take positive or negative value depending on which side you want to control the voltage. So this is basically like a citation system, but design is much easier. Okay, so the transformer, the type position, it can be moved by a discrete number of positions. Each position corresponds to maybe a small percentage of voltage change. For instance, if this transformer can vary voltage by 10%, okay, so you have 16 type positions. Those 16 type positions will divide that 10%. So each one roughly will give you maybe a few percentage to change the voltage. If it has unload type changer, so you can connect this one in this closed loop control system, so you can automatically adjust the type position. That's why we call such transformers as active voltage controllers. So typically it's used to control the secondary voltage, and it can be just near the secondary side, or it's on the far location based on the load drop compensation component. But I have to emphasize the transformer is not the source of reactive power. It is something you can utilize to control voltage, but it's not the source of reactive power. Why? Because the transformer entirely has no capacitance. Maybe that's not 100% accurate, but the transformer eventually is just a writer. It's one type of adjustable writer. It can change in the voltage. But if you consider all the voltages in per unit value, the transformer basically just maybe adjust the local readings. So which means the transformer itself is a reactive load. It's not a reactive source. Well, how can it increase voltage? Because it borrows some reactive power from the primary side and give it to the secondary side. It's like a broker in the stock market, okay? So it do some investment for you, but you need to pay a price. If you want to gain more, but you need to pay more price, more service fee to the broker, okay? But it doesn't generate the money from nothing. It actually borrows something. It just charges some reactive power here. So in order to make sure the type changing is successful, which means you can regulate the voltage to the direction you desire, to either increase or decrease. You need to make sure you have sufficient reactive power available on the primary side. If the primary side doesn't have any reactive power, even the primary side also lack reactive power, that will be an issue. So when you increase the type position up, okay, so when you increase up, so the Q going to the secondary side, this one will also, right? Should go up, but the condition is the primary side need to have enough Q. But if the primary side is very weak, and this Q doesn't necessarily go up, this is it's a very large drawback for using type changing transformer in voltage stability control. Because you expect to, when you design this feedback control, negative feedback control, you determine moving up will bring more Q to the secondary side and then support voltage. Okay, so you just keep that same direction. But if the primary side is very weak and the Q cannot increase, like primary side will almost reach a limit, the Q cannot further increase, but the type doesn't know, it will keep moving. Okay, it can go to the opposite. In order to really explain this, what happened, we can wait until the voltage stability session, because that will cause some bifurcation issue, which means the direction of the control actually change, but the controller doesn't know. Okay, so the operator, if operator believe the primary side on the left-hand side not strong enough, you need to disable this control manually, or you have some other algorithm you can decide when to disable the type changing transformer. So type changing transformer under normal condition, it does give you voltage regulation, but under emergency condition, they are usually the first thing you need to disable under the voltage stability concerns. Okay, so let's see one example. So if this is like type changing transformer, so it's operated at 345 kV on the primary side, 138 kV on the secondary side. For neutral position, the secondary side will operate at 138 kV. Okay, assume the secondary side has some load require 2 megawatt ready power, and the primary side need to provide that amount. So you can do the math, right? 5 in and 2 out, which means 3 megawatt is consumed by the transformer itself. That's why it's like broker. It charges some money from you. Okay. So now we want, let's say if we want to increase the secondary side voltage from a 138 kV to increase to, based on the calculation, we want to move up by 5 type position. So this is totally 16 type position. So 5 divided by 16 multiplied by 10%, which means I supposed to have 3% increase of voltage, which gave me a 142.3 kV. But when you implement this type changing, you definitely get more ready power on the secondary side, but it's not as much as you really want. Okay, the secondary side will only reach up to 141 kV, right? Slightly less. And now the load consume 6 megawatt. The source provide 10 megawatt, and the transformer itself will take 4 megawatt. It will charge more. Okay. The third condition, if you want to further increase the voltage to 150 kV, based on your calculation, you need to move up to the end, right, to utilize all the 16 positions. But eventually, you only get 146 kV. Okay. And the transformer itself right now consume 7 megawatt. Okay. So if the primary side already reached the limit, definitely for this case, you already utilized all the 16 position. But if you still have room to continue moving up, but the primary side has no ready power to provide, it will stop there. And when you continue moving up position, what happens? That will increase the total reactance of the transformer. And the total reactance plus the load will, the total, if you treat the transformer and also the load entirely as a load, this load impedance will increase. And that will make the primary side voltage to further drop. Okay. So this one can be easily explained, but where I will leave more discussion to the voltage stability session. But a quick answer is, if the source has a constant voltage source, has some internal reactance, and the load has some impedance, which is changing, okay? When the load is changing, that can cause the voltage to change. Okay. Next one is easier. That's a synchronous condenser. Synchronous condenser, it can be dedicated equipment to control voltage, or it can be simply just a synchronous generator. Some synchronous generator operating in the condenser or motor mode, which means it doesn't generate any IT power, but still have the full excitation control system you can utilize to regulate voltage. So it basically just a synchronous generators or machines without prime mover, without input mechanical power. But it can utilize a little bit power just to balance its rotation. It can provide inertia to the system, and it still has the excitation system we have discussed in this section that can provide voltage regulation. It can have like AVR, automatic voltage regulation. It can be connected to a tertiary winding of a transformer, which means they may not be required all the time, but if needed, they will just through that tertiary winding to inject or consume VARs. To have a dedicated synchronous condenser can be very expensive because there's the manufacturing or the deployment can be similar to synchronous machine. But they can have a lot of benefit. They can regulate voltage. They can also help regulate frequency because they don't generate any active power, but they have like a inertia. The inertia can slow down the frequency drop under emergency. Some utility just retire some thermal unit, such as the coal-fired power plant. If they retire this power plant, it still take that location. They still have the whole control system they can utilize, so they can change, remodel this the power plant, thermal power plant as synchronous condenser. Okay, yeah. Definitely some hydro unit can definitely operate as motor, or if it's like pump storage, it can also operate as synchronous condenser. Okay. And when you have more and more renewables in the system, and you need to have spending reserve. Remembering the dark chart we talked about. Okay, if the solar need to drop within 1 or 2 hours quickly, you need to have some generation to pick up. So those generation, it's better they are just spinning there, and they can easily increase their output by the low frequency control. So such unit under that condition, if they're not providing any power, but they're running there, they can be utilized as synchronous condensers. Another very useful thing for synchronous condenser is now to it's not about the practical operational design, it's about the research. So if you have some research work, you want to study voltage control. So there are many different controllers, right? They have a shunt capacitor, shunt regulator. You can have many. Later we'll talk about another tool based on power electronics. But usually those control devices are more complex. So if you want to first verify whether the idea is good or not, to place the voltage controller there, one very easy method is just place synchronous condenser there. So in your model, okay, if you decide I want to add some voltage controller, automatic controller at those locations, but I want to verify those locations are good or bad, you can put the synchronous condenser there. Basically just synchronous generator, but without prime mover. The input in mechanical power will be 0, and output also 0. Okay, they only just utilize. You still have a exciter, but you don't have governor. You don't have any other turbine, those model. But you keep the detailed synchronous generator model, and together with exciter model, and you just, because synchronous condenser has much better performance than any other controllers. So if that can verify your concept, then you can move to each individual controllers for voltage. So which means most of the following other voltage controllers, they try to emulate what a synchronous condenser does, even they may not be perfect. So one type is called static var compensator. A static var compensator, it is a var source, but it has no spinning part. It has no rotor. Basically just like this one. It's just combination of many regulators or capacitor. You can decide to adjust the regulator or switch in or switch out capacitor to give you the desired var. Okay. Static just means there's no rotating part, but it can behave similar to a synchronous condenser. So usually each SVC can have shunt regulators, capacitors. They will be switching not by mechanical switches, but by power electronics, like high-speed resistor-based switches, so you can control remotely. They have a control system very similar to automatic voltage regulation for generator. They can either control the location near the controller or far from there if you have load compensation component. So this one is a figure from the April tutorial. If you read that chapter about voltage control, I have more details on how to design or deploy or how operate such system. But this is very good illustration, give you idea on what SVC need to have. So it has this is a sequencer controlled writer, and this is like a sequencer controlled capacitor, right? They have a number of capacitor, and this is also writer. This is like control system similar to AVR. It can measure the voltage. So here only assume you measure voltage, but if you want to add load compensation, you can also measure the current. So you have a PT, CT, and CT both to as the measurements. So the control system will switch those sequencer-based controllers because there's a lot of writers, capacitors, and also power electronics. So there may be a high order harmonics. So you really need to have some filter. The filter just try to filter out some harmonics. So you can also connect the SVC with like a switchable capacitor banks, a switchable writer bank, and also connect to some like transformer, so you can make it be a more complex system. So you can call it like static VAR system. One example is just if you combine SVC with unload type changing transformer, and you can make this design. Okay, so this pretty much still based on SVC. You can make it have a more complex design, and because this transformer can also adjust the tap positions. To study how such static VAR system control the voltage, we can use this simple model. So here at the location where this system is placed, it will have at least two shunt branches. One has adjustable inductance, the other has adjustable capacitance. Okay, and assume you have perfect controller. Okay, that can quickly implement the desired inductance or capacitance into the system. Okay, and such as you can smoothly transition from reactive load to reactive source. So that will be able to maintain the voltage at terminal flight. That's ideal control. You can smoothly transition from like a more capacitive type of load to a more inductive type of load with either leading power factor or lagging power factor. So that's ideal case. Okay, so the voltage doesn't change with current. A current can be either positive or negative. But in reality, it's not easy to have adjustable capacitor. It doesn't mean you cannot adjust capacitor but adjusting capacitor is much harder than adjusting writer. Okay, because if you have any chance to see adjustable capacitance, the capacitance, in order to have a very large capacitor, you are utilizing the surface of the capacitance. Okay. So in order to adjust capacitance, you have to change the surface. Let's assume you have two surfaces covering each other, and by changing the angle, the overlapped area, so you can decide the capacitance. If you have a very large capacitor, that's very hard to adjust. I remember I went to a museum, they have a really high voltage capacitance. You can try. You have to push very hard to adjust the capacitance. It may be fine for like an offline adjustment, but it's not good for automatic control. So a very practical idea is basically I just have maybe a single capacitor, but I do have a adjustable writer. Adjustable writer is much easier. You're just sliding how much reactance you actually you are going to put into the system. So you just add an adjustable writer in parallel with just a fixed capacitance. By using the adjustable writer only, so you are going to operate on the lagging power factor. Okay, you're going to operate on this quadrant, the first quadrant in the plan for the voltage versus current. Okay, so you're going to, for example, this can be one inductance, this can be another inductance. So by adjusting the inductance, you can smoothly changing along this line to make a voltage almost flat. Then you can add this phase capacitance. So its leading power factor is operate on the left-hand side. When you add them together, finally, you can operate along this line. All right, so if the control is very fast, then you can make that line to have almost zero slope, almost flat, which means the voltage can be controlled within very narrow range. This is more practical state-of-the-art system. But this system has a lot of drawback. The drawback is if you can make sure to operate within this operating area, that can guarantee the voltage to be controlled around the setting point. But what if you reach the limit, you are going to either follow this line to move or follow this line to move. That will suddenly change the voltage. Okay, you just imagine you involve this system in your automatic control, and under normal condition, the voltage will be very close to nominal value. But sometimes it just reaches the limit, but you don't know. If further control, it will suddenly drop. That can be very bad if you have a lot of disturbance, especially when the disturbance has like short circuit near this controller. The voltage can be very low, and it cannot give you the rated power you want. So once it reaches the limit, it will downgrade to just a regular shunt capacitor or regular shunt director. Okay, which means their VAR is not. It will be proportional to V squared. It's like a shunt capacitor. It still gave you some rated power. It still operate in the second quadrant, but it will follow the characteristic like a shunt capacitor. So if you use this simple model to study how the voltage can change, the left-hand side is just equivalent for the rest of the system with internal maybe voltage and with internal readings. And this SVS or SVC will behave like a adjustable reactive load. All right, so let's see. Now let's assume it has a single adjustable reactor and with maybe 3 capacitors in the parallel connection. So for condition number 1, okay, I need the entire adjustable reactor, but only just first capacitor. So that will give you this will give you this characteristic. Which means if you maintain the voltage within this narrow range, that can make sure the voltage to be controlled. But once it reaches the limit, it will downgrade to just shunt capacitor. Okay, so let's see if the voltage drop to, so this line, this straight line with negative slope just indicate the that's a system condition. The system condition will intersect with this SVC characteristic. That will be the operating point. So when the system loading increase, so this one the voltage drop, it will maybe drop to this line, right? So that line will intersect with the SVC at this point. So if the voltage further drop, it will follow this line. The voltage will drop quickly. Then you need to switch to condition number 2. So once you switch to condition number 2, you somehow extend the operating region by a little to here, but it's still not enough. So you have to further switch in the older capacitor. So that will give you a bigger range to maintain the voltage. But what if the load further decline? Then it will out of the limit, and then you will so this then the voltage will drop quickly. So this first rectangular area indicate the maximal VAR you can provide by condition number 1. Okay, and this bigger area indicate the maximal VAR you can provide by switching all the capacitors in. So this is actually the maximal capacitance, the capacitance or maximal ready power you can provide. If you need more, it will just decline following that that line to drop the voltage quickly. Okay. So there will be 2 stages. So if you operate within the range of the control for the SVC, the voltage is almost like constant, and so the ready power only depends on the current. It's proportional to the current. But once it reaches the limit, and further, if you operate beyond the limit, the ready power will be proportional to the voltage square, just like a passive controller. So within the rectangular area, it's proportional to current, but outside the limit will be, this will be the total VAR. So that's proportional to voltage square. Okay, so why do we care about the range, operating range of the SVC? Because under some conditions, we need a lot of VAR, okay, and it's secured, very stable, a very reliable VAR to the system during a very short amount of time. That is under the fault-induced delayed voltage recovery issues. So this term, the feed VAR, sometimes it also called transient voltage stability, but which is very confusing terminology, because this one doesn't really involve any mechanism from voltage stability. So later when we talk about voltage stability, that's totally different mechanism. So the IEEE Power and Energy Society has discouraged the use of this terminology. So don't call it transient voltage stability. But if you read any paper published before 2021, if they talk about transient voltage stability, don't be surprised. Okay. So this is from the real event, a real feedback event that happened in Southern California, Edison, back to 2013. So the red line indicates the actual voltage. You can tell. So after the event happened, it take about 20 seconds to recover back to the value of the nominal voltage, and then you have overshoot. They have the voltage become higher by 6%, and that lasts for a long time. Then finally, it will go back, but it will stay under voltage for a long time. So this is one story showing the lack of a dynamic controller like a synchronous condenser, SVC, such type of device. But if you only just utilize capacitors, writers, try to support voltage or limit voltage, you may not be fast enough. Okay, the system will have either under voltage or higher or over voltage. So you see what happened is when the voltage is recovered, but the capacitor still stay on the line. It's not just it does provide additional VAR to support voltage, but they will stay at higher voltage. Then they just switch off the capacitor, but then the voltage will drop to be under the nominal value. Okay, so if you have some dynamic controller, like a synchronous condenser, SVC, that will be able to mitigate this issue. So that can make maybe the voltage drop can recover faster, and they will stay around nominal value. So a NERC has some standard about the what dynamic voltage you need to have under any contingency. So we mentioned this one before. This is from NERC standard. It gave you just standard the voltage waveform right after any fault. So it considers 3 stages. The first stage is up during when the fault is when the fault happened and it's clear how quickly you can recover the voltage back. And next we'll look into the oscillation of the voltage waveform to make sure the waveform will stay within an envelope. And the third stage will check the steady state condition. For the steady state condition, it will go into an even narrow range. So there will be stage 1, stage 2, and stage 3. Okay. Like for instance, in the standard, it may require the voltage dip not exceed 25% at low bus, 30% at non-low buses, which means for those transmission substation, you never see the voltage, which is like a 0.7 per unit. Okay, so that can be very bad. Even just temporarily, that can cause a lot of issue. If your voltage drop to 0.8, not 0.7, but it stay longer than 20 cycle, okay? Like this duration is longer than 20 cycle. That's also bad. Okay, you need to limit that one. When you get to the third stage, the steady state voltage should not exceed 5%. So that's why typically if you saw power flow, you study steady state condition, the voltage on the transmission network need to be from 0.95 to 1.05. So usually 5% variation. Such problem can be mitigated by SVC. And another device is called STATCOM. Actually, they're much better than SVC. What is a STATCOM? The STATCOM is a static synchronous compensator. The old name is, if you read very old literature, they can call it STATCOM, STATCOM. That's called static synchronous condenser. But now the name is STATCOM. The difference from the SVC is it has some internal voltage source, so that can give you the constant current. That can make sure even you reach the limit, the VAR still proportional to voltage, not proportional to voltage square. So the VAR will change as a linear function of voltage, not a quadratic function of the voltage. That's better. Okay. In normal condition, it behaves similar to SVC. The design can be very simple. Basically, that DC source that can give you try to provide like constant current, and through the inverter, from DC to AC, and it will just inject reactive power. Okay. So if you only look at this figure, it's pretty much like a inverter-based resource. This design is very similar to most of like a solar farm, a wind farm. When you connect the renewable energy to the grid through a power electronics inverter, but which means inverter-based resources have been there for a long time, but these are not for generating any power. It just try to provide reactive power, which also means you can easily make inverter-based resources for solar or wind energy to behave like a STATCOM. Okay, they can easily operate as STATCOM. So question will be the manufacturer operator, they really desire them to operate as STATCOM. Okay, operate as STATCOM, which means under some conditions or in some operation mode, the main purpose is to provide reactive power, to provide a high inductive current to the system, but not as a capacitive current to the system. But that may not be a good for maybe the life or maybe the condition for this renewable energy resources. So utility do place dedicated STATCOM in there. It can be very expensive. Okay, so to compare with SVC, SVC is that characteristic. So let me highlight, maybe use different color. So this is SVC, right? We already explained this one. Within the operation region, it will maintain the voltage flat, but out of the region, it will downgrade to a shunt capacitors. The reactive power will change as a quadratic function of voltage. But because STATCOM can maintain constant current at the limit, so it will give you more reactive power. So when the the operating condition down, like, let me see. This is like operating condition, right? Intercept this point. So when it move down. So for SVC, it will operate at this point, but for STATCOM, it will have this one. So if you compare the two area, all right. So SVC has much less ready power to the system because it will be quadratic function. The ready power will decline as quadratic function of voltage. But STATCOM can maintain that large rectangular area. Even it's still decreased, but it's a linear function of voltage because of the constant current. If you compare the performance of a STATCOM versus SVC, so the first curve indicating some like delayed voltage recovery problem. This is from that paper. That paper is was published around the same time as that Southern California Edison event. But during that time, there are very high percentage of air conditioner load in the southwest area. The air conditioner load based on induction motor, right? The induction motor has stalling effect. In the load modeling, we mentioned if the induction motor stalled, that will, do you remember how should we model induction motor if we don't want to put differential equation? Right, somehow like so if it's at the normal voltage, so the induction motor behave like what? Constant, either constant power, constant current load. But if it's stalled, it will behave like a constant impedance load with very bad power factor, right? Remembering or something like that in the load modeling session. Okay, so that is the cause of the delay voltage recovery problem. So if you put the SVC there, it can mitigate the problem, but it still have some risk to stay too long at low voltage. So STATCOM will be much better. All right. Okay, so this is my last slide for voltage control and regulation. And any question? All right, no, so we will move to next session. Let's switch to a small signal stability session. So in the control system of the voltage control and regulation figure about the generators, I mentioned there's many controller and many blocks, but there's one thing I didn't explain. I said I'm going to leave that one to next session. Okay, we'll first need to address that problem. Do you remember what that is? What I have not covered by the voltage control regulation session? That is power system stabilizer, right? Sometimes I put the first, so the first item, the effect of excitation control on angular stability to the voltage regulation control session. Sometimes I just decide to leave it in this the small signal stability session, because if we talk about the power system stabilizer in the voltage section, that will give you some wrong feeling. We don't need this section at all. right? Because we have addressed everything by excitation system. Because the excitation system is going to cause some small signal stability concern, but that one can be addressed by power system stabilizer. Okay, so if I cover this material in that session, and you may feel, okay, this session is not important, but no. The most important thing for this session is to talk about the small signal stability analysis methods. Those methods are very important. But because if you don't know those methods, you only feel you can rely on the power system stabilizer to address the small signal stability problem. That's not true. That can give you a wrong feeling. So if you want to propose any small signal stability controller in your research, in your dissertation, you always want to rely on the power system stabilizer. Okay, you always want to maybe revise or upgrade or maybe utilize the idea from a power system stabilizer. That may not always work. I had the experience in some presentations. They talk about using the solar farm to help to improve the damping of oscillation, and they directly borrow the power system stabilizer there. Okay, but first you need to understand why do we need the power system stabilizer. It's not like a unified controller which always give you positive damping. You have to utilize correctly. Okay, the power system stabilizer is designed in such a way because they try to compensate some effect from exciters. Okay, that's what we're going to talk about. So we'll first cover that part which was left over from previous session. Then we'll focus on the small signal stability analysis for both simple system like a single machine feedback system and the multi-machine system. Let's first talk about what effect excitation control can have on the angular stability of a generator or a power system. So this is swing equation. Swing equation it's based on just the second law, Newton's second law. And the right-hand side will be the difference between the mechanical torque and electric torque. And variation of electric torque has two components. Okay, the first component we call it delta TS, second the delta TD. The first one we call it a synchronizing torque component. The second is damping torque component. So why do we call them in this way? Because they can be approximated by a term either proportional to the angle deviation or the speed deviation. So if it's a linearly changed with angle deviation, that part component is called a synchronizing torque. Otherwise, it will be synchronizing, or it will be damping torque. Okay, then let's see how to come out with those coefficient, Ks or Kd. So Ks can come from two places. The first one is from a generator together with network. A second, it comes with the design of the excitation system. And similarly, damping torque coefficient comes from the generator network, which means outside of the excitation system. The second is the excitation system. So why do we have to split in such a way? Because for any power system or generators, if they're well designed, the first component has to be positive. Otherwise, you have some design problem. So we in today's system, we don't worry about the first component to be positive and negative, but second component can be a question. Okay. So if we don't have exciter at all, we have a constant field voltage or constant field current, which is equivalent to have the gain, the Ka in the AVR to be 0. Okay, or you may just make it a very small number. It doesn't do any control at all. Then there will be two scenarios. The first one is you will have either positive synchronizing torque and a positive damping torque. Which means if you try to draw the deviation of the electric torque in the plane about the speed deviation and speed deviation and angle deviation is in the first quadrant. It has positive projections to both axes. So if you have both positive, a stable waveform of a generator will like this one. By stable, which means it finally will go to some new equilibrium point, right? It will get closer, and also the amplitude is declining. It will have positive damping. So you have positive synchronizing torque and positive damping torque. Under some conditions, the system may become unstable. If it becomes unstable, the deviation will increase. It won't just stay at a limited value. But the envelope of the waveform, it will still become smaller and smaller, which means you have positive damping, but negative synchronizing torque. Okay, so now you feel, okay, that's definitely not good. I don't want this generator to lose stability. So maybe I can utilize excitation control to enhance the stability. So if you add a very strong excitation control, you still have two scenarios. One is stable, the other is unstable. So for stable, it still behave like same. So this one basically same as the first case. It go to the new equilibrium and also has positive damping, which means you get closer to the equilibrium point. But if your system become unstable, you have positive synchronizing torque but negative damping torque. Positive synchronizing torque, which means the center point will basically stay on the equilibrium, but the waveform will have bigger and bigger amplitude. All right, so that's a dilemma we're facing. Maybe I have a generator, so it can either stable or unstable. If I have no excitation control, the generator can fly away and there's some large disturbance, but the damping may be fine. But if it's fly away, the waveform will have smaller amplitude, but if the generator flies away, it causes some out of state issue. That's definitely bad. If I use the excitation control to enforce the synchronizing torque, which means it will stay close to the equilibrium, but the waveform can be growing, right? The amplitude can be growing. So I either face the first one is more like a transient stability problem, or I can face like damping problem, like small signal stability problem. This is what we are going to address, okay, by introducing the power system stabilizer. I stopped here for a second because those waveforms are very useful. If you simulate a very large system, okay, and there's some disturbance, and you see many generators become stable, and there are few of generators become unstable. If you see any generator behave like this one, what does that mean? That generator has very weak excitation control. If you want to make that generator be more stable, you need to try increasing the gain. If you allow to adjust the model, that will definitely better. Will bring this system generator more stable. But if you see any generator like this one, which means the excitation may be too strong for that generator. But definitely, if you decrease the Ka, that can switch to the first condition, right? Therefore, it can switch to this condition. So if you jump between those two conditions, the generator always become unstable. Either just is flying away from the rest of the system, or it's at growing oscillation, which means you do need the PSS. Okay, that's a very important trick for you to make a system stable. So because if you work on large system models from utilities and you add some disturbances, it may not be easy to make all generators be stable, okay? And for those unstable generators, they can fall into those two conditions. You can try adjust some parameter. If that's just for research purpose, you want to first create a stable system, then test your idea, right? You first need to make system stable first. So let's figure out how to determine the effect from a citation system. So a citation system mainly determines the two coefficients, right? Ks depend on the change of the excitation, which is the flux linkage of the field winding, or the Kd depend on the change on the field winding. So if we draw the first component, only the electric torque depend on the change of the flux linkage in the field winding. So it will have two components. So the sign of those two components will be very critical, because the Ks or Kd depend on the generator, the network usually positive, because if the system is well designed. So those are usually positive, but those are unknown. Those two items are what we need to figure out. All right, so if you go to the Quinter's book, the chapter 12.4, there's one section to derive this block diagram. You should be able to do that on your own without looking at that chapter, based on what you learn from the generator modeling section and also the excitation system section. Okay, you just put all the equation there and try to draw the block diagram, and you should be able to finish this one. But if you don't want to do that, you just read this section. Oh, you don't want to read the section, you just believe me. Okay, this is correct. Okay, because we want to just find some small signal, small disturbance cases, so we can somehow linearize or ignore any limits or saturation or nonlinear components. So it will be like this one. So the question will be how angle deviation or speed deviation can affect the excitation, which is actually the flux linkage in the field winding. So based on this block diagram, you can have this transfer function. The transfer function will be from this angle all the way until here. Okay, if you write the transfer function based on all the channel, you can start from angle to the flux linkage, you will get that transfer function. Okay, so now we can, based on that, we can, and the next one, we need to go from the flux linkage to the electric torque. So basically just add another component, so it will have this transfer function. This tells you how the electric torque change with the angle if you only have flux linkage changing. Okay, that's a transfer function we want. We want to figure out what those coefficients are. So usually the AVR of the generator has some effects on the damping or synchronizing torque components, and the two most critical coefficient or the component in the transfer function will be K5, and this the model of the exciter. K5 is here, exciter is there. Why? Because those two appear here, right? Depend on the range of the value. Remember one thing we discussed. So when we model the AVR, the excitation system, most of the K factor is around 1. There's only one component which is much larger than the other, because that's gain. That's Ka. Ka is the inside of this exciter, right? Definitely this exciter has more complex transfer function, but if we only want to figure out the sign, either positive or negative of those two coefficients, we can just use very simple exciter model, basically just first order component with just Ka. Okay, so the exciter basically just Ka. And here it basically just K5 multiplied by Ka. And those two, this product can be much bigger than any others in the numerator. Okay, so that will make a, so we can somehow figure out what value we need to use for Ka. K is the only thing we need to decide, because we need to make sure this entire transfer function in this pink color to be positive, because we want to make sure the synchronizing torque to be positive. But here there's a negative sign, so which means we have to make those two to be negative. And because K cannot be negative, K5 has to be negative. If K5 is negative and under steady state condition, so that transfer function will become this one. So we just let S be 0, okay? And this one has to be positive. That answers the question. So if we have negative K5, we can make the synchronizing torque to be positive, which means it will, if the disturbance is not too large, it will stay around the equilibrium, okay? Because near the equilibrium, you have the force driving the generator back to the equilibrium. That addresses the question like synchronizing torque, but we haven't answered the damping torque. Let's assume dynamic condition. So for dynamic condition, I don't want to make it complex. I only consider what if the dynamics only have one dominant oscillation mode, which means the waveform basically like a sinusoidal waveform at frequency this omega oscillation. But we don't know. Let's keep it open, okay? For this case, we need to plug in this J omega into that transfer function. I don't go to the detailed step, but if you do it, you just plug in that J omega into each S in that transfer function. And the nice thing is you want to, but the entire transfer function is just coefficient of delta, because now you plug in an imaginary number that will create some real part and some imaginary part. Assume we have real part and imaginary part. They both multiplying the angle deviation. Okay, we definitely know this part will be synchronizing torque, but this one will be question. But synchronizing torque means there's a component which is in parallel with the direction of angle deviation, which means if the angle deviation change following some waveform, that torque component changing in the same direction. They're not like lagging or leading, but or opposite. They're always in the same direction. But this part is a question because it has a J in there. J is just imaginary number. J will introduce a 90 degree. Okay, so how do we determine how the second component? So there's one approach we can do it. So if we multiply the J delta delta by this oscillation frequency and then divide it by this oscillation frequency, J multiplied by the frequency will be S. Is that clear? Okay, because we assume that one to be S. So right now the dominant frequency, this is dominant frequency, and this part is dominant frequency. So that one will become S. So in frequency domain, S multiplied by delta delta will be delta delta dot, then divided by frequency. Then delta delta dot is delta omega. Delta omega R is speed deviation. All right, so this guy is actually just the speed deviation multiplied by a factor. That factor is just the synchronous frequency divided by oscillation frequency. If your synchronous frequency is 60 Hertz, oscillation frequency is 6 Hertz, so that number will be 10. You can like a 10 multiplying the speed deviation. Okay, so we get the conclusion. So if we plug in the oscillation frequency into that transfer function and do such a simplification, eventually we will get two items. The first item is synchronizing torque. Second is a damping torque. And the damping coefficient is exactly just the imaginary part multiplied by the synchronous frequency divided by oscillation frequency. then we get the conclusion. We know the synchronizing and damping torque coefficients. So this approach is good for a specific frequency, okay? Which means if this frequency, this omega oscillating, this frequency is what you're really interested in, you use this method to calculate the synchronizing and damping torque coefficient. But if you want to study a different frequency, you have to redo again. You plug in a different frequency. So the same design of the excitation system can have different damping for different oscillating mode. Okay, you want to make sure each mode has positive damping, have a small signal stability. You need to try this approach on every mode of interest. I have a paper a few years ago. I follow exactly the same approach to study the cause of the sub-signals oscillation caused by wind farm. Even that's not for signal generator, it follows the exactly same idea. Because for the wind farm, you know the oscillation can be caused by some component. You design a transfer function similar to that one. So for generator, definitely that transfer function is from the angle deviation to the electric torque, electric power. But for wind farm, you can have such transfer function maybe from voltage, current to something else. And then you have this transfer function, and you can plug in the oscillation frequency J omega, then you study the damping and the synchronizing torque. Okay, synchronizing torque telling you whether this wind farm can operate together with rest of system easily. And damping torque tell you if this is oscillating, whether the oscillation will be growing amplitude, will have a declining amplitude. So you can use exactly the same approach to do that study. Okay. So this is very critical. So we understand under static condition, S equals 0, so we plug in 0, so we have the synchronizing torque. Because at the static condition, there's no oscillation. We don't worry about damping. But if the system is oscillating at this frequency, we need to plug in J omega oscillating. So real part will be the synchronizing torque. Imaginary part will, after some correction, will have the damping torque. So there's one example from a Kunder's book. It gives you some typical value. So you see this K5 take a negative value in order to make sure the synchronizing torque to be a positive. Under static condition, you plug in all let S be 0, that will give you this one. So if you make the synchronizing torque to be positive, and you need to make sure the numerator to be positive, right? You can determine the minimal value for Ka. The K need to be large enough. If the system is oscillating, assume it can oscillate at 10 radian per second. 10 radian per second is about 1.59 hertz. Then you need to plug in this one into the transfer function, okay? I don't go into the detail, but I give you a table by taking different the control gain. Like 0 means you have no excitation control. If you have no excitation control, this one becomes negative. But the damping coefficient is positive. So you want to address this negative synchronizing torque. That's why you want to increase the gain. And you eventually will make a positive synchronizing torque. Okay, but the damping torque becomes negative. Okay, for this case, because also have the K1 also contribute the total synchronizing torque. So finally, you have good synchronizing torque, but damping torque can be bad. All right, so next thing will need to be addressed by PSS. So PSS is going to make sure even you have a large gain, and how can make sure this one to be positive. That's going to be addressed by PSS. So we'll talk about that next Tuesday. All right, okay.